Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the course consists of several critical topics. And one of those topics is convolutional neural networks, which is topic number 7 in the list of topics. And the subtopic is B. So, slightly more difficult concepts as compared to the easy concepts of 7A. So, this is 7B. And this video uses the supplemental website available at www.ezmcq.com/GoGet, which is a personalized learning management system. The approach adopted in this course is based upon content delivery, and the features of that content delivery are listed on your screen. And this is ahead of the traditional slides based approach. And this approach is literally used by hundreds of millions of online users throughout the world. And based upon that content delivery, we have developed the personalized learning management system. In green color is the URL of the personalized learning management system, and it consists of several features. The key 6 features are shown and demonstrated in 6 videos. The URL of those videos is shown on the screen in blue color. So, what are those features? For example, full text search in the content of all the questions and answers, and ability to support people having handicap or disability or some limitation of viewing, so they can send or set the color, size of the font, spacing, and so on. And it optimizes the limited space of the smart handheld devices in a hierarchy of the content. And then, of course, you can also track your progress so that you know what you have done and what you need to do. And there is the facility of online testing and grading and evaluation of results. And of course, this is centered around the question and answer based approach, which is engaging, which is thought provoking, which is very powerful, which is proactive also, and the details of the traditional approach. So it's the best of both worlds, and it is a blending of these two technologies and techniques. So in front of you is the list of topics which are covered in this course, and we are at topic number 7. That topic is convolutional neural networks, and the contents of this topic are on your screen now. Every question and answer is a concept. So those concepts are divided into groups. So the lecture number 7A grouping is shown in yellow color, and the next grouping in green color, and so on. So the difficulty from yellow to purple increases progressively. Now, without further ado, now we move on towards the actual lecture. So, what constitutes the architecture of CNNs? Well, uh, in deep reinforcement learning, convolutional networks or CNNs process high dimensional visual input like game frames and images, which we have discussed. Now, acting as feature extractors, CNNs transform pixel data into meaningful representation, okay, and which is used by a policy, okay, which makes their architecture crucial for learning efficiency. So, in this concept or Q&A, we will look at what constitutes the architecture of CNN. Okay, so this is the basic architecture, right, which consists of the input layer and the output layer, and in between we have the convolutional layer. We have the polling, which we discussed. So these are the from here we extract the features, and then we have here where we perform the classification. Now observe that this is fully connected because that is beyond CNN. CNN is not fully connected. All right. So let's cover this in detail. So we have the convolutional layer, the activation function, okay, which is included within the feature extraction, and the pooling layer, which is also included. And then we have this fully connected network and the normalization layer. So what happens is that the final features are flattened, final features as we move ahead, and fed to a fully connected layer, and which generates the outputs like deep reinforcement learning. Now we can maybe add batch normalization layers, which further stabilizes the training. How? By keeping input distributions consistent across the layers. So some layers are not overloaded, and some are less. So each layer in the CNN contributes to effective feature extraction. Effective feature extraction, each layer, and learning stability. Now, if this is done properly, it improves both the sample efficiency and the training performance, right? In deep reinforcement learning tasks. So what it does is enhances the agent's ability to generalize. So the key word here is generalize across different environments. So what we'll be covering is in front of you. So what is a convolutional layer? That extracts meaningful spatial features. How? Using filters. We have already discussed the filters. And what it does, it enables the translation invariance. Okay. And it ensures efficient learning with less or fewer parameters. And this basically is the basis of visual understanding in deep reinforcement learning. So activation function that adds non-linearity. How it helps is that it helps in, or it allows in learning complex patterns, and that learning of complex patterns is essential for accurate function approximation in value or policy networks as in reinforcement learning. Now, pooling layer, as we move beyond the convolutional layers, pooling layers downsamples feature maps to reduce the complexity or to let go of the unnecessary details. Now, this helps the network focus on dominant or large values or dominant signals, and it that helps to generalize better. Okay, so what is why and where? Why and where fully connected networks are used? These process flattened features to make the decision. Flattened features which come from the pooling layers and connects the CNN outputs to deep reinforcement learning specific tasks like action selection or value estimation. Alright, so that's why we need them for making decisions. Basically, it's not making decisions, but it's like more of a decision support. Okay. Normalization layer. So the normalization layer stabilizes and accelerates training by normalizing the activation. All right. And how it does that? It supports deeper networks and improves the learning dynamics. That's how it works. So the details of what all we have discussed are here: convolution layer, activation function, pooling layer, and normalization layer also. And if you're interested, here are the further references. So why are CNNs suitable for visual input in especially for reinforcement learning environments? Now, typically, CNNs are ideal for processing visual input, which we have seen, especially for reinforcement learning, which we will cover subsequently, what reinforcement learning is. Why it's possible? It is due to the ability of CNN to extract structured features from high dimensional data, like images or video frames, which could be coming as input to a reinforcement learning system like a robot or a driverless vehicle. So, in reinforcement learning, agents rely on visual observations to make decisions. Okay, and CNNs convert raw pixels into meaningful and spatial representations that support this process. So, how this process is supported is through the spatial hierarchy, which the CNNs create out of the video or the image, and the parameter efficiency. Instead of whole lot of working with parameters, work with a kind of a subset of the parameters. And of course, there are other things also. But before I go into the details, so there are quite a few details present here, which we will cover. So, what is the major advantage? The major advantage of the spatial hierarchy is that the early layers of CNN, okay, the beginning layers, they capture the basic features like edges and so on, while the deeper layers, which proceed towards the final layer, they learn abstract patterns such as shapes or the textures or the environments. Now, this is just like mimicking how humans perceive, and that helps the agent as in a robotic vehicle or a driverless car or a robot, interpret their surroundings. Now, as you this is the kind of environment we are looking at, right? So we have an autonomous vehicle which has to pick this can of a drink, and then the image is going in. This is the vision module, and then is the deep remote learning module, which we have covered, and then an action takes place, and based upon that action, okay, action takes place at time t, and based upon that action, there is a change of state at time t plus 1, and hopefully there is a reward to the action at time t plus 1. So this is how it's working. So now, so this is, we can see there's a major advantage in the spatial hierarchy, right? Now CNNs are also parameter efficient, right? How? Because the local receptive fields and the shared weights result into uh, converting larger inputs with fewer parameters. That's the biggest advantage. Now, translational invariance, I will go into details, makes them robust to small positional shifts of the objects, like this object being considered, in dynamic reinforcement learning settings, and so on. So, let's go into more details. So, spatial hierarchy we have covered, but I will redo it. So, CNNs build layered feature presentations or representations. What it does, it enables the agents to understand the visual environments. How? From the basic edges to the full objects. Now that helps in more informed decision making. More decision making as the robot decides how to say grasp a certain object in reinforcement learning. So remember, decision making is different from decision support. Parameter efficiency. CNNs use fewer parameters. How? By sharing the weights across input regions and making them efficient for large visual data. And of course, they automatically identify the parameters of interest, which is suitable for real time reinforcement learning applications where time is critical. All right. Translation invariance. Now, CNNs can recognize patterns irrespective of their location, regardless of their location, which allows the agents to respond consistently without variability to visually similar states. So, for example, the angle of the can is slightly rotated, so it will kind of recognize it. So this allows working in states across different frames or environments. That's the flexibility. Feature extraction. CNNs learn to identify key features automatically. So there is no feature engineering by a human in the loop. And how it does it extracts those features from the raw images. So what is the outcome? It reduces the need for manual pre-processing. And what it does, it improves the policy learning in a complex settings. So what is policy? That we will discuss in reinforcement learning. And finally, the scalability support. Let me scalability support. CNNs can handle high resolution and complex inputs effectively without corresponding dramatic increases in the complexity of the hardware or the memory requirements. So what it does, it ensures performance and they remain stable as the environment grow in detail. So it kind of it is like not kind of, but so it is scalable. So if you're interested in details, Here are the details of what all I have discussed. So you should read those details. And if you're interested in references, here are the references. So now we move to the next Q&A of this video lecture. So it's not that like CNNs are a panacea and they have only the benefits. They have some limitations also. And in this Q&A, we will look at the benefits and the limitations of using CNNs in deep reinforcement learning agents. So what we'll be covering are these are the bullets, and of course there are more bullets also. I'm sorry, there are more details of these bullets, and further details are given. So this image here, now there are a number of issues or shortcomings of CNNs. Now this image is specifically for generalization. Okay, so this basically in the red box is the kind of identification which was in error, right? This is in the red box which was in error. This is the actual, right? And this is of course generalization, and this is the true which was identified by specialization. All right, so let's go over this. So CNNs are crucial. There's no doubt about it. The CNNs are crucial in deep reinforcement learning, especially when dealing with visual or spatial inputs like images or videos. Now, CNNs automatically extract the hierarchical features in the image or the video, and as a consequence, they reduce the need for manual feature engineering. So it's very fast, it is less prone to error, and it helps the agents understand the complex environments. So what CNNs do is they capture the spatial hierarchies along with the local patterns. How it is done? Through that sliding filters, which we already discussed. Now this enables the CNNs to detect shapes, features, and textures and objects regardless of their position. So that is how that robotic vehicle could get hold of that can of the drink, irrespective of its position or location. Now, this spatial invariance improves the robustness and efficiency in tasks like robotics and gaming, which I just discussed. Furthermore, CNNs use fewer parameters as opposed to artificial neural networks due to parameter sharing and local connections. As a consequence, this helps in reduction of overfitting, reduction in memory requirement. But CNNs can be computationally demanding to train, obviously with large inputs and action spaces, where action is taking place in the space. So as a consequence, it slows down the learning, right? And it's not very good for real-time use. So now let's look at the bullets. Feature extraction. I'm sorry. Feature extraction. CNNs, the one of the biggest strengths of CNNs is that CNNs automatically extract useful spatial features from raw visual input, and that reduces the need for manual feature engineering, and it improves the learning efficiency, especially for deep reinforcement learning agents. Spatial invariance. Now, because of the convolutional operations, CNNs are enabled to recognize patterns regardless of their position. As a consequence, they become, which makes them effective in environments where or with dynamic or moving visual elements, like for example used in autonomous or driverless vehicles on a kind of a busy street. Parameter efficiency. CNNs use fewer parameters. How? By sharing weights across the location, and which makes them efficient to train, requiring less computation power, requiring less energy, and Not only those two benefits, but less prone to overfitting, specifically in reinforcement learning contexts. Training complexity. Okay. Now, CNN introduced additional complexity in training, additional requiring more computational resources and careful hyperparameter training. I'm sorry, tuning, which could be, of course, challenging. So there has to be balance between the features extraction and the training complexity. There has to be a trade-off, and of course, the generalization issues. While CNNs perform quite well in trained environments, but they sometimes struggle to generalize to new ones. And what it does, it limits their utility in varied or evolving deep reinforcement learning scenarios, as can be visualized in this image, where frisbees are considered as, I'm sorry, let me clean this. So, frisbees are considered as yo yos, and this gentleman is considered as a specific person. And well, I cannot differentiate myself between a toad and a frog, but this is basically a frog, not a toad. And this teapot is was erroneously selected as a teapot. So the reference of this image is given in the references. Details are here. Here are the details about those bullets. Here are the references, and this last one, I believe, is the reference we just looked at. So now we move on to the next Q&A.